This video I want to discuss first of all the Carnot cycle and then the Rankine cycle, but before I do that I want to go into a few concepts and review them again just so we are clear about those concepts, and then it would be easier for us to understand the Carnot cycle and the Rankine cycle as well. I'm going to start off with the most basic concepts in thermodynamics. The zeroth law of thermodynamics, which tells us that if two systems are in contact with each other and they are in equilibrium when it comes to temperature, and they're in contact with the third system as well, then both of those two systems are in equilibrium with each other as well. And this is the most basic law of thermodynamics. It's by intuition as well. We can imagine that if we have a system A and that is in contact with, let's say, system B, and these two are in thermal equilibrium, and then we have a system C and this is in contact with system B and in thermal equilibrium with system B, then what that means is that system A and C are going to be in thermal equilibrium as well with each other. Okay, that is what the zeroth law of thermodynamics tells us. Then we've got the first law of thermodynamics, that is also known as the law of conservation of energy. What it tells us is that the energy is always going to remain conserved. It's not going to be created, not going to be destroyed. The total energy of the system is going to remain the same. In mathematical terms, what the first law of thermodynamics can be written as is that the internal energy, and we're especially talking about closed systems right now, that the internal energy of a closed system is going to be equal to the net heat transfer into the system, which is represented by Q, and the net work done on the system, which is represented by W. We're just going to have to make sure that we check the sign conventions here, which is why W is being denoted by minus here, and Q is being denoted by a plus here. Okay, so I'm reviewing this because on the basis of this, then you can imagine that every process follows the first law of thermodynamics. So whether we're talking about adiabatic processes, or we're talking about isothermal processes, or isobaric processes, all of them have to obey the first law of thermodynamics. So you can work out from the first law of thermodynamics what an isothermal process, for example, what's that going to mean? Okay, and then you can transform that onto a figure as well on the PV diagram, let's say. So that is what the first law of thermodynamics is. And then the second law of thermodynamics, it has different statements. The two most basic ones are the Clausius statements and the Kelvin-Planck statement. The Clausius statement, what it tells us is that it is impossible for any system to operate in a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. This is the statement. The focus is on the sole result. Okay. So what do we usually see in daily life? That if we have a hot body, it can transfer its energy to a cold body, right? That is what happens. This is a spontaneous process. It occurs without any external help, right? So heat transfer can take place from a hotter to a cooler body, but heat transfer cannot take place from a cooler to a hotter body by itself. Yes, heat transfer can take place from a cooler body to a hotter body, but not spontaneously. That means that there has to be some external effect that should also be taking place. Some other effect within the system or the surroundings, or both. That means we could provide some energy over here in order for us to maybe do some work and extract energy out of the cooler body into a hotter body. Okay, this is what it means. That heat by itself cannot flow from a cooler body to a hotter body. Okay, the example, for example, if you're looking at refrigerators to cool food, refrigerators supply cooling to hot bodies, right? They're themselves supplying energy to, let's say, fruits. So fruits are hotter, you buy them outside, you bring them in, you put them in the refrigerator. Now, the refrigerator is supplying um, cooling to a hotter body, but they have to be driven by electric motors. So the Clausius statement implies that it is impossible to construct a refrigeration cycle that would operate without a power input, right? And that is also why this statement is known as the refrigeration and heat pump statement. Then we've got the Kelvin-Planck statement. And before we talk about the Kelvin-Planck statement, we need to understand what this term thermal reservoir means. It's a special kind of ideal system that always remains at a constant temperature, even though energy is being added or removed through it by heat transfer. So what the Kelvin-Planck statement says is that it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. What that means is that the amount of energy that is given to a system is always greater than the amount of work done by the system. Okay? So net transfer of energy to the system is possible, or net work can be zero, but the work done across the cycle is going to be equal to or less than zero for a single reservoir system. Okay, we could have two reservoirs here. If there was a reservoir here, and we were extracting work out of it, but then we were also, there was some kind of energy that we couldn't use to drive the cycle. That is possible, but it's not possible for us to extract heat content out of this thermal reservoir and convert all of that heat into work. That is what the Kelvin-Planck statement indicates. And that is what we usually see with engines. That's why this is also known as the heat engine statement. And now that leads us to an important concept, entropy. But before we go to entropy, you should go and review how to use steam tables. I'm going to leave the link in the top right corner of this video as well. You should understand how you can use steam tables to extract different properties out of it. But the second law is what leads us to the concept of entropy. And how do we usually define entropy? That it is a measure of disorder. But I feel that it is not, that's not a good definition, because what does disorder mean? I mean, if you were looking at a glass of water, and if you were looking at a glass that was full of ice, which one would you think is more disordered? You just think to yourself. I would think, for example, that the glass of ice is more disordered, but it has less entropy. So what does this term disorder mean? It's not clear. So it's a popular one-line definition that is usually taught, but it's harder to understand it just by the definition. Yes, it could be the correct definition if you went into the mathematics of it, from the Clausius inequality to Gibbs free energy, and you would get the relationship between temperature, enthalpy, and entropy, and then you could define disorder. But to understand what entropy is, without going too deep into those concepts, we're going to go with another definition. That is that entropy is a measure of how spread out the energy is. And keep in mind for now, because first we need to see why or how entropy was discovered in the first place, and that is because of the Industrial Revolution. More than 150 years ago, engines were being constructed, and the quest was to make these engines more efficient. And an engine's efficiency is deeply related to its entropy. So you know how an engine works, right? You put fuel in and burn this fuel. It's going to create heat somehow, and then somehow this heat is going to be turned into the movement of the engine. But there is a very subtle point here, that it's not actually heat that is being created that runs the engine, but it is a difference in the temperature. It is a difference in the temperature which moves the engine. So if you were, let's say, I'm going to simplify this and just give you an example of, let's say we're looking at two plates that are right next to each other. and one of these plates is cold, one of these is hot. So what you don't see is the heat going from one plate to another if they're already in equilibrium. What you see is that eventually both of them are going to come to a state where they're going to be in thermal equilibrium with each other. The colder body is going to get a bit hotter, the hotter body is going to get a bit colder, and then we're going to be at a thermal equilibrium and nothing is going to happen anymore. So how about an engine? If, for example, if we're looking at different types of engines, if I'm looking at an engine that has, let's say, it's running on, you've got one plate here, you've got a second plate here, you've got air in the middle, and you're heating up this plate, let's say. You're heating up this plate, it heats up the air, and then the hotter air moves up, the cooler air moves down. This cooler plate hots up because of the hotter air next to it, okay? And then because this is heating up now, it's gonna start a process where it's gonna create movement, and then it's gonna move the shaft, and the engine is gonna start moving, right? So that is how an engine works, that you need a difference in temperature. Now, it's entirely possible that this body, the one that I'm talking about is hotter, is not actually hot, it's cold. But then this body is colder than this cold body, right? But there's a temperature difference that still exists. Because the point that I'm trying to make here is, what if both of these plates were hot? What's going to happen then? Nothing is going to happen, right? So that means that there needs to exist a temperature difference rather than a transfer of heat that's going to drive the engine. Okay. So that means that the energy is useful only if it is clumped together. If the energy is being clumped together in this plate, it's useful to us in order for us to heat up this plate. If the energy is spread out, as it is over here, that's not of any use to us, right? Because the energy has spread out and you cannot use it anymore. So that's why I feel that there's a better definition going with this, that entropy is a measure of how spread out the energy is. And entropy always increases, and that means that energy is always spreading out, that it is going from a clumped up state to a spread out state. So now we're just going to look at what thermal efficiency is. Efficiency, what that means is, even in layman terms, what it means is that the energy that you supply into any system, you get whatever you get out of it, the ratio of the net work done to heat that you're supplying. That's thermal efficiency. Okay. And for power cycles, because we're only going to look at power cycles in this lecture video, for power cycles, the net work done by the system is the output that we require. Okay. So if you look at this diagram, what's happening is that the energy is being transferred from a higher temperature source to a lower temperature level. Okay, QH over here is the heat energy that is being transferred into the system. This is our system being represented by the dotted lines. So QH is the heat content that is being transferred into the system, and QC is the heat energy that is being dissipated by the system. That means that this energy, QC, is not being used by the system. So what does that mean? That QH minus QC is the energy that is being used and converted into the form of work, right? So another thing that we already know is that thermal efficiency of power cycles is always going to be less than 1. And what that means is that QC is equal to 0 is not possible. Because what that means is that the thermal efficiency of that cycle will be 100%. That means that whatever energy is being transferred into the system is being converted entirely into work. And we already saw that that is not possible because of the Kelvin-Planck statement. So QC cannot be equal to 0, right? So the thermal efficiency is work done across the cycle by heat content that is being supplied into the system. And because work done across the cycle is equal to QH minus QC, we can simplify this equation into this form. Okay. And if we were looking at the thermal efficiency of a reversible power cycle, then according to the Kelvin scale, all we can say is that QC over QH of a reversible cycle, this is for a reversible cycle, is equal to Tc by Th. And T over here indicates the temperature. Tc is the temperature of the cold reservoir, Th is the temperature of the hot reservoir. So the ideal thermal efficiency of a reversible power cycle is going to be equal to 1 minus Tc by Th. 1 minus Qc by Qh is the thermal efficiency of an irreversible power cycle. Okay, so this is the maximum thermal efficiency that can be achieved. And the maximum thermal efficiency, this second expression over here, is known as the Carnot efficiency. Okay, so we already talked about why QC cannot be equal to 0, and this expression over here is Carnot efficiency. What I want you to do is that I want you to go ahead and get on Excel and plot this equation. Fix, let's say, a temperature for Tc, and fix an array of, let's say, different temperatures, 10 different temperatures as Th, and see what the maximum efficiency is that you're going to get. Okay, so usually these things would be discussed after discussing the Carnot cycle, but I'm discussing this first because I wanted you to know how the thermal efficiency for any power cycle can be worked out. And now we can move on and look at the Carnot cycle. Okay, so it's the most ideal kind of cycle there is. Maximum efficiency that can be achieved is through a Carnot cycle. And it's an ideal cycle. Realistically, in actual life, we cannot, have a system that operates on Carnot cycle, but I'm going to talk about that in a minute. With Carnot cycle, we can have either gas or vapor that can be utilized as a working fluid. And I'm just going to show you the Carnot power cycle that is being executed by a gas as a working fluid. And through this piston cylinder arrangement, what we see is that 1 to 2, we talk about adiabatic compression. And what's happening here is that the gas is being compressed, which means that the pressure is increasing. So the process is adiabatic though, and that means that although no heat is entering or leaving into the system, the temperature can still increase. Then for process 2 to 3, what's happening here is that the system, the piston cylinder assembly, is placed in contact with this hot reservoir. It's at a higher temperature Th, and the gas then expands because heat content is being supplied into the system. And the gas expands, that means the volume is increasing isothermally though. Isothermally, that means the temperature remains constant while receiving heat energy, QH. And then you've got process 3 to 4, in which the piston cylinder arrangement is again placed on the insulating stand, and now the gas is allowed to expand more steadily. And the gas is allowed to expand, which means the volume is increasing further, although it's increasing adiabatically, which means no heat exchange is taking place. But the gas is expanding, so that means the pressure is lowering and the temperature is lowering as well. Then from 4 to 1, we've got our assembly that is now placed in contact with a lower temperature reservoir, Tc, and the gas here is being compressed here, so the volume is decreasing and the pressure, that means, is steadily increasing isothermally, so the temperature remains constant until the initial state is achieved, for which heat energy needs to be released, which is QC. So this is all the information that we need in order for us to translate all of this information onto a PV diagram or a TS diagram. Okay. So we've got the processes, and we're talking about a reversible Carnot cycle. So process 1 to 2 is a reversible and adiabatic process. It's compression that is taking place. So that means that the volume is going to reduce. And if I was to look at the PV diagram, that is what's happening here. From 1 to 2, the volume is steadily decreasing. And it's an adiabatic process, so it's a bit steeper like this, less steeper than the isothermal process though. From 2 to 3, 1 to 2 is more steeper than an isothermal process. You can see that here, right? 2 to 3 is an isothermal process. It's expanding as well. So that means that the volume is going to increase, and the volume is increasing in this direction. And 3 to 4, you've got a reversible adiabatic expansion now. So the volume is going to steadily increase now, and you're going to arrive at state 4. And from state 4 to 1, you're going to have a constant temperature heat rejection that is taking place. It's an isothermal process as well, so the temperature remains constant. And because it is being compressed, so compression means that the volume is going to decrease, and the volume is going to be decreasing in this direction. Okay, so this is your PV diagram. If you were to draw it onto a TS diagram, the process 1 to 2 is taking place where it's going from state 1 to state 2, which is at a higher temperature, TH, if you remember from the assembly that I just showed you. And from 2 to 3, then the temperature remains constant because it's an isothermal expansion. Okay, and then 3 to 4 is an isentropic process, so the entropy is constant here, and 4 to 1 is then an isothermal process. So you might think here that, hang on, how do I know that, for example, process 1 to 2 is an isentropic process? An isentropic process is an idealized thermodynamic process that is both reversible and adiabatic as well. And that is what process 1 to 2 is, that it is reversible and it is adiabatic as well. So that means, hence, it's going to be isentropic as well. And the same goes for 3 to 4 over here, for which it's reversible and it's adiabatic as well. And hence, it's going to be isentropic as well. And we've already talked about the thermal efficiency. That's the same thing over here as well. This is the Cardinal efficiency, the maximum thermal efficiency that can be achieved. The subscripts, obviously TC and TL, they're the same. TC represents the cold reservoir temperature and TL represents the lower temperature reservoir. They're the same thing. So this is what I was talking about, that the efficiency is always going to be higher for a Carnot cycle as compared to an actual realized cycle. So why do we use it then? The purpose of it is that it gives us a higher ceiling of any system, that this is the maximum efficiency the system can achieve and nothing beyond that. Okay, so that's the first. And the second thing is that it gives us basically what it gives us is it gives us the motivation to make our systems better as much as we can in order for us to maximize the efficiency as much as possible. Although we know that, for example, if for a Carnot cycle, if we had a system where we could see that the maximum thermal efficiency that can be achieved for that cycle is, this is just an example, let's say it's 80%. Okay, this is the Carnot efficiency over here, let's say. Then if we have a real-life system that gives us an efficiency of, let's say, 35%, then the Carnot cycle, what it's telling us is that, hang on, you can actually make this efficiency better somehow by adding more auxiliaries into our systems. And that means that I can bring this efficiency to, let's say, around 45% by adding a couple of more things into my system. And then I can still be like, oh, okay, hang on, I can actually make the system even better. And I can try and bring it up to 60% or 65%, 70%. So that is what the Carnot cycle gives us. It gives us a maximum achievable efficiency this is the efficiency that cannot be achieved by any cycle. Okay, this is the ideal efficiency. So you can imagine that because of losses and everything, the efficiency of an actual cycle is going to be lower than this value, but how much lower? Then that is dependent on how efficient our systems are. So that was the Carnot cycle that we looked at that had the working fluid as a gas. If we were using water or vapors, then that would be the Cardinal vapor cycle. And then you've got these four systems in here. The boiler, what's it doing is that it's changing the phase. Phase change is taking place here from liquid over here to vapor. So you're providing heat. It's converting water into a vapor, okay, because of this temperature or the heat content that is being added. Okay. So you've got steam then at state 1. Then this steam is expanded adiabatically through the turbine, and work is developed through this turbine. So the temperature decreases and the pressure decreases as well. Over here, the temperature was constant, the pressure was constant. Over here, the temperature is decreasing and the pressure is decreasing as well. Then, after the turbine, through the condenser, heat transfer takes place to the cold reservoir. So the steam is then converted into a water vapor mixture, a liquid vapor mixture at state 2, because obviously energy has been extracted out of steam in this turbine. So at state 2 now, you're going to have a liquid vapor mixture here. And some of that vapor is going to condense, and that is going to be that is because energy is being taken out of the liquid vapor mixture. Okay. And as this water then passes through the condenser, it is received into the pump. So the pump receives this two-phase liquid vapor mixture from the condenser, and it returns it adiabatically to the state at the boiler entrance, which is at 4. Okay. So you're doing this work over here to increase the pressure. So the pressure is increasing from state 3 to 4. Okay. And the temperature is increasing from Tc to Th. So I just want you to take a minute and go ahead and try to identify how this entire cycle is going to look like on a PV diagram. So if you're doing that, just go ahead and pause the video right here. And once you start playing it again, I'm going to show you how this cycle is going to be represented onto a PV diagram. So if you're back now, I'll just show you now. You've got 4 to 1. The temperature was constant and the pressure was constant as well. So that means it's going to be a straight horizontal line from 4 to 1. At 1, what I told you was that it's converted entirely into steam. At 4, what I told you was that it is in the form of a liquid. Okay, so you've got this curve on, so you've got, let's say, a critical point over here, and to the left side of this critical point, you've got the saturated liquid line, and to the right of this point, you've got the saturated vapor curve. Okay, so that means if you had a state that was on this side of the curve, then that means that it would be completely liquid. So because the temperature and pressure remains constant, you move horizontally on this PV diagram, and you get to state 1, and at state 1, you've got steam here, vapor, okay, 100% vapor here. That's why you're on this line and not inside or outside of it. And then from state 1 to 2, you've got turbine, which is extracting work out of this steam, and then you're left with a liquid vapor mixture. So then it drops inside this dome, okay, and then the temperature is decreasing here, the pressure is decreasing as well. So you get to state 2 here, and that is at temperature Tc, okay, at the lower temperature. So that's how you get to state 2. And from state 2 to state 3, again, your temperature remains constant, your pressure remains constant as the water is passing, as the water vapor mixture is passing through the condenser, okay, until you've now basically decreased the vapor content in the water vapor mixture. And now from 3 to 4, you've got a pump which is converting this liquid vapor mixture into a liquid and increasing its pressure and thus increasing the temperature as well from Tc to Th. So that is what the Carnot cycle was about, and now we're going to move on to the Rankine cycle. The real Rankine cycle that is used in power plants is a lot more complex than a simple ideal Rankine cycle. It is by far the most widely used cycle for electric power generation even today, so that is where we're going to start. You've got Rankine cycle, that is a vapor liquid cycle. So it's usually water, but not always. We're going to look at water right now. And other than that, what you should know is that it consists of, obviously, right now we're looking at the ideal Rankine cycle, first of all. Okay, then we're going to look at the modifications as well. So for an ideal Rankine cycle, before we dive into that, we need to look at our components and we need to analyze them as well. Okay, so you've got a turbine, you've got a condenser, a pump, and a boiler. I'm going to start off with the turbine. So let's just look at this turbine first. You've got vapor that is coming from the boiler at state 1 at a higher temperature and pressure, and then that expands through the turbine to produce work, and then it is discharged to the condenser at state 2, which is at a lower pressure. And we're going to treat this turbine as a control volume, and onto this control volume then, by using the basics of thermodynamics, we can apply an energy balance across this control volume. Okay, we can apply the mass balance onto it, the energy balance onto it, the energy rate balance onto it. I'm going to leave a video here on the top right hand corner for you if you haven't gone through that yet, but you should go through that, how you can apply the energy rate balance onto a turbine. And this is your basic equation that you have for a steady state analysis. Okay, so the left hand side is 0 because it's steady state. The Q dot is 0 as well over here. You've got obviously work that is being done, so that stays. M dot into H1 minus H2 plus your kinetic energy term here and the potential energy term here. The kinetic energy term and the potential energy terms are usually neglected for a turbine, so these go to 0. And then from this is the equation that you get. That in order for you to find out the work done across the turbine per unit mass, or per mass flow rate, you can go ahead and just find out the enthalpies at state 1 and state 2, and that is good enough. That's going to give you the work done. Okay, and just like that, if you were to apply for a condenser, it would be Q out is going to be equal to H2 minus H3. Okay. You should see one thing here, that over here you had H1 minus H2, which was initial minus final value. Over here, for a condenser, you've got H2 minus H3, again, initial minus final. For a pump over here, you've got H4 minus H3, which is final minus initial. And for a boiler, again, you've got H1 minus H4, which is final minus initial value. And that is because, and this is a good way to remember the subscripts that you're going to use for the components. For work done, you're extracting work out. Okay. For a condenser, you're taking heat out of the system. So then for these two, you're going to have initial minus final values. Whereas for a pump and a boiler, you're putting work into the system, And that's why you're going to have final minus initial over here. You're putting the heat content into the system, and that's why it's going to be final value minus initial value, which is H1 minus H4. Okay. And now, if you were to look at the efficiency for this cycle, it's going to be, the efficiency is going to be equal to what we saw before, work done across the cycle divided by Q in, okay? Or you could write W dot by Q dot, and then from here, you just have to plug in the values of enthalpies, and that's how you can find out the efficiency, the thermal efficiency of the cycle, okay? You could do it that way, or if you were looking to do it in the form of heat contents, you could also do it that way as well. Okay, so that's how you can find out the efficiency of a Rankine cycle. Another important performance parameter is the back work ratio, which means that what is the amount of work that you're putting into the system and what is the amount of work you're extracting out. Okay, so obviously you have to input some kind of work into the system here through the pump, and then you're getting or extracting work done out of the turbine. So that's going to tell you how much energy you're inputting into the system compared to how much energy you're extracting out of it. And that's called the back work ratio. And before we move on to looking at the Rankine cycle on a PV and a TS diagram, I'm just going to look at this PV diagram again and tell you what this means. On this PV diagram, on this side, this is obviously what we just discussed. It's the saturated liquid line, okay? The area behind this, towards this side, is the subcooled liquid region. And you got the critical point, that's the maximum temperature at which a substance can exist as a liquid and as a vapor together. Okay, that's the maximum temperature. This side of the curve, it's called the saturated vapor line, and beyond this dome, you've got the superheated vapor region. Okay. Within the dome, you've got the two-phase liquid vapor mixture region. Whereas if you were looking at the TS diagram, you're going to see that you've got temperature on y-axis and you've got entropy on x-axis. Again, you've got a saturated liquid line, saturated vapor line, just as it was in the PV diagram. You've got a critical point here as well. You've got the constant pressure lines, and you've got the constant specific volume lines as well. Okay? And the constant specific volume lines, you're going to see here that they have a steeper slope as compared to the constant pressure lines. Then you've got the constant quality lines that are shown within the two-phase liquid vapor region. Also, what you will see is that in the superheated region on the TS diagram, which is on this side, the constant enthalpy lines, which is being represented by H, they almost become horizontal as you start reducing the pressure, as you can see here, or you can see here. Okay, as you're reducing the pressure, okay, and you're going to see that they start becoming horizontal. And this is being shown in this shaded region over here. So for these states where this region is being shown as a shaded area, what this shows you is that enthalpy is a function of temperature only. So you can just look at the temperature within this region, and across the temperature in this tables, let's say, you can find out what the enthalpy is. Whereas outside of the shaded region, enthalpy depends on the temperature and the pressure value as well. Okay? So you need to look at both these values, let's say over here, but in the shaded region, beyond this, over here, You can just look at the temperature and find out the enthalpy across it. So now we can go ahead and we can look at the Rankine cycle, the ideal Rankine cycle. Right now we're not looking at the actual Rankine cycle. So for an ideal Rankine cycle, for a saturated ideal Rankine cycle, there's 4 reversible processes that are taking place. Process 1 to 2 is taking place across the turbine. Okay, so you've got state 1 over here, and you got state 2 that is over here. Turbine across this, you've got, because it's an ideal cycle, so it's reversible as well. So that means you've got a reversible process, an isentropic process, an isentropic expansion that is taking place of the working fluid through the turbine. Okay. And the exhaust at 2 is usually a 2-phase liquid vapor mixture. Okay. So on the PV and the TS diagram, just go ahead and think what this is going to look like. Because it is an isentropic process, what that means is that it is reversible and it is adiabatic as well. Okay. And we already know that state 1 is steam, it's vapor. So it's going to start off on this line, okay? And from here, because it's adiabatic, then it's going to have a steeper slope. It's going to move down to the temperature of the condenser, okay? Just like that on the TS diagram, from state 1 to 2, you're going to move vertically down because it's an isentropic expansion, and you're going to arrive at state 2 over here at the condenser temperature. Okay. So from 2 to 3, across the condenser now, you've got heat rejection that is taking place. You've got 2 over here, you got 3 over here, you've got an isobaric heat rejection that is taking place. It's happening at a constant temperature, and being a 2-phase mixture now at 2, as we previously saw, the constant pressure heat rejection takes place in the condenser. Okay, so because the pressure is constant, it's an isobaric process, so it's going to be a straight and horizontal line on the PV diagram. And on the TS diagram, again, it's going to be a horizontal line, because what we saw from the TS diagram was that the pressure lines are horizontal on the TS diagram within this 2-phase liquid vapor mixture region. Okay. So that is happening across the condenser. Then for the pump, process 3 to 4, you've got adiabatic compression that is taking place by the pump of the liquid, of the saturated liquid at the condenser pressure. And now we're going to look at that. What's that going to look like? So you got 1 to 2 and 2 to 3, and then 3 to 4. What's happening is that you've got an isentropic compression that is taking place now. Okay, and at state 3, what did you have? You had saturated liquid. Okay, so because of the pump now, adiabatic compression takes place across this pump of the saturated liquid, which was at condenser pressure 3, to a subcooled liquid region now at state 4. Okay, and this is at the steam generator or the boiler pressure now, 4. Okay, and line 3 to 4 is vertical on both diagrams because liquid is incompressible. Okay, and the pump is doing this process in a reversible manner. Okay, it's an ideal process that we're looking at. So because it's isentropic on the TS diagram, then it's going to be vertical as well. Okay. From 4 to 1 for the boiler now, it's isobaric heat addition. So isobaric means that it's going to have a constant pressure. Okay, but you're supplying heat into the fluid now. We've got constant pressure heat addition that is taking place in the steam generator or the boiler now here. Okay, And what's going to happen is now that 4 to 1 is going to be a horizontal line. Okay. Whereas on the TS diagram, what it shows you is that from 4 until this point, okay, or from 4 until this point, let's call this point B. Okay. Let's call this point B. So from 4 to B, it represents that you're bringing the subcooled liquid at 4 to a saturated liquid at B. Okay. And that is why this is called a steam generator over here instead of a boiler now. Because the process of 4 to B takes place within the steam generator in a component called an economizer that is a part of the steam generator. Okay, it's an economizer, it's called an economizer, and from 4 to B, it brings the subcooled liquid to a saturated liquid at B. Okay, within the economizer, it's part of the steam generator. And from B to 1 now, from process B to 1, you're gonna have, what B to 1 represents is that heating of the saturated liquid to a saturated vapor at constant pressure and temperature. Okay. And now this B to 1 is taking place within the boiler, or it's also called an evaporator as well. So that's why it's called a steam generator, because it has two components. It has an economizer, and an economizer process 4 to B happens, and in boiler process B to 1 takes place. Okay. So just to complete this cycle now, a cycle is when you go back and rejoin at the initial state. Okay, then it's going to be a cycle. So this is what in an ideal Rankine cycle looks like. You've got 4 components. You've got a turbine, you've got a condenser, you've got a pump, and you've got a steam generator as well. Now, this was the saturated Rankine cycle. Okay, that means that the initial state was that of a saturated vapor. But the problem with this is that it's possible that once this vapor starts interacting with the turbine, the liquid particles starts developing in there. Okay, the liquid particles start developing in the turbine, and then that can be harmful for your turbine blades. So then you can make a modification in your Rankine cycle, and instead of having a saturated vapor entering the turbine at state 1 over here or here, you've got a superheated vapor that's going to enter into the turbine, and that's being represented by state 1 dash over here. So what's going to happen? Again, everything is going to remain the same for a superheated ideal Rankine cycle, except that your states are going to shift. So from 1 to 1 dash, from 2 to 2 dash, 3 to 4, and 4 to 1 remain the same. Okay. So this helps us then that we've got a superheated vapor that is entering into the turbine. It's not going to damage your blades. You're going to get a higher efficiency as well. Okay. So this is what I was talking about as well, that when the Carnot cycle gives you an upper limit, now the saturated Rankine cycle gave you a certain kind of efficiency. You wanted to increase that efficiency. So one of the ways of doing that is by superheating the Rankine cycle, because now the area under the curve is higher. So the work produced is across 1 dash to 2 dash, right? Across the turbine. So that means the value H1 minus H2 for the turbine, which is your work done basically, is going to be higher, right? That was W dot T by M dot. So the work done is going to be higher for 1 dash to 2 dash as compared to 1 to 2, right? Whereas across the pump, W dot P remains the same. Okay. So that is, what does that mean? That means that the efficiency for a superheated ideal Rankine cycle is going to be higher as compared to the saturated Rankine cycle, saturated ideal Rankine cycle. Okay. So this is what we already talked about. You can use the same analysis for each component. You're adding heat QA into the system across the steam generator, okay, across 4 to 1, so that's H1 minus H4. The turbine work is happening across 1 to 2, so it's H1 minus H2 or H1 dash minus H2 dash. You got heat that is being rejected, that is H2 minus H3 or H2 dash minus H3, and pump work is H4 minus H3, and then you can evaluate the net work done over here. Okay, so I'm going to leave you with that, and in the next video we're going to look at an example of a Rankine cycle.